So we're doing problem number 3 here, and the first step is to show all the forces in the force body diagram. And so for the bucket, we're going to have a force of gravity, mg, and then we're going to have a tension force, T1. For the pulley itself, we're going to have the gravitational force of the pulley, big mg. We've got a tension force pulling down, and since it's the same rope, I'm going to call that T1. And then I've got a force of a string pulling upward, so I'll call that tension force T2. Okay, so in this next question, I just transferred the force body diagrams to this new page so I had more room, and I'm trying to find the linear acceleration of the bucket. And so I know that that linear acceleration is going to be the same as the acceleration that the pulley rotates. So I'm going to use the sum of the forces for the bucket first, and that would be mg if I call this the positive direction and this. Actually, let me think. In terms of the diagram, if down is positive, then this direction would be positive. Okay, so we've got mg minus T1 is equal to ma. Oh, and here's something that is a common error that I always make, which I'm sure happens to some of you as well, is when you've got big M's and little m's, sometimes you are careless about the distinguishing between the two, but it can really ruin your solution. So I'm working with the bucket, so I need to make sure I have lowercase m. Now I'm going to do the sum of the torque equation for the pulley here. And in this one, I'm going to have T1 creating the torque, and that's in the positive direction, times a radius r is equal to the inertia times alpha, which I know is A over r. And then from there, I always like to reduce things, and I end up with T1 is equal to 1/2 ma. I can plug T1 into here, and I get mg minus 1/2 big ma is equal to little ma, and then bring my a's together. And isolate the A. And then from there, I can just divide to the other side. So I've got mg all over m plus big M over 2, and that would be your final answer. In this next question, we're trying to solve for the angular acceleration. So alpha is equal to RA, and actually no, that's wrong. A is equal to R alpha, and so since we're solving for alpha, it's A over R. So what I'm going to do first is I've got a fraction here, so if I multiply top and bottom by 2, I can get rid of that fraction. So A is equal to 2mg over 2m plus big M. Divide that by r, and you get 2mg all over r times 2m plus big M. And that would be your angular acceleration. Okay, so we're going to find the tension of the force on the rope. I left this equation here because I have T1 there. What we could also use, actually I think this might be easier, is we had an equation for the pulley. The sum of the torque was equal to the tension times radius equals 1/2 mr squared A over r. And that actually gives us a much easier equation because remember all these r's canceled out, and T1 was equal to 1/2 ma. So let me plug in my A from up here, mg all over m plus m over 2, And I, again, don't like working with fractions, so I'm going to multiply 2 on top, 2 on the bottom. That gets rid of this 1/2. And then I get big M, little mg. And then if I distribute this 2 to each side, I get 2m plus m. And I believe that is your answer for tension 1. All right, so the next step is to find the speed of the bucket at the end of distance h. This one I can tell right off the bat is going to be a kinematic problem. My speed that I'm solving for is we'll just call it V final is equal to V. And then V initial is equal to 0 because it starts at rest. My distance, delta y, is equal to h. And my acceleration is equal to mg all over, I'm going to make this 2m plus m to avoid fractions. Okay, and from there I can use the V final equation, the V final squared equation, and I'm going to start with 0 initial velocity, and V final is equal to the square root of 2 times a, which is mg all over 2m plus m, times h. And I don't think you can really simplify that anymore. All right, so for part F, we are trying to find tension 2, the force exerted on the pulley by the axle. And so I'm going to use the sum of the forces of this force body diagram. I've got mg pulling downward. So I'm going to call that a negative, and tension 1 is also negative, plus T2, and since the pulley isn't moving up or down, that acceleration is 0. T2 is equal to T1 plus mg, and T1 we got as big M little mg all over 2m plus big M, and then add mg to that. You can leave it like this, but if you want to get it into the same answer as the answer key, just factor out a big mg. You get little m over 2m plus big M plus 1. And that would be your tension 2.